Welcome to Brain Vision.
All right, so this is a pretty long problem, so just go ahead and get ready and buckle in for a bit of a ride. So we have an inclined plane, and at the bottom of the slope, we have a mass, capital M, which is tied to a string. The string goes over a pulley at the other end, which goes down the vertical side of height h and is tied at the bottom. The string has a mass little m, and the angle of the plane is theta. And that is all the symbols that were given at the beginning. And then we have to do a lot of just finding different values of different relationships between the variables and different physical quantities. So the first part of the question, part A, asks us what analysis model we can use for the mass big M at the bottom of the plane. And the answer for this is we can treat it as a particle under constant acceleration. So particle under constant A, and that's really all you have to say for the first one. We know that we can treat it as a particle under constant acceleration because that's what we did when we were dealing with these kinds of acceleration problems and these force diagrams in previous chapters in previous work, where we just analyze the dynamics of the forces acting on the box or the weight, whatever you want to call it. So yeah, so that is our analysis for the weight m. Part B asks us for the analysis model for the vertical part of the string, because in this problem we are also concerned with the standing waves that form in the vertical part of the string. And for this vertical part, the waves can be described as standing waves with boundary conditions. And we can go ahead. We know this because it's bound at both ends. So at the bottom, it's tied to the table or whatever it's on, and at the top, it's going over the pulley. So we know that it has a boundary condition there as well. So I'm just going to write it. I'm going to write condition with a bit of a shorthand there. So yeah, that is our analysis model for the vertical part of the string. So that's parts A and B, but we still have to do parts C through I. So we got a lot of work to do. A and B are the easiest parts of the problem. So in part C, we're trying to figure out what the tension is in this string. And we know that there's tension because the string is stretched, over the pulley, and the weight is pulling it down. It's at rest at the bottom of the inclined plane. So we know that it's pulling on the string, and it's also tied at the other end. So we have to figure out what the tension force is. And the way that we do that, the easiest way, I think, is to just do a force diagram on the mass big M. So if we take, just our plane, and we draw our box, so we have three forces acting on it. We have the tension from the string, which is what we're trying to find. We have the normal force supplied by the inclined plane, so I'm going to call that Fn. And then we have the force of gravity acting on the box, which is going straight down, and that's Fg. So the easiest way to kind of think about this is by looking at the forces that are perpendicular and parallel to the inclined plane. So Fn and T are already in that coordinate system nice and neatly. Fn is perpendicular and T is parallel, but Fg is not, so we have to decompose that a little bit. So we can look at Fg by drawing it like this. So here is Fg, here is our plane, and then here is the perpendicular component and the parallel component. And here's a right I'm going to redraw this because it ended up a bit messy. Perpendicular, parallel component, right angle. There we go. So we're trying to find T. We know that all the forces balance because the mass is not moving. We're trying to find T, which is parallel to the inclined plane. So we're concerned with this component here, the parallel component of FG. We know by doing a little bit of analysis that this angle here is going to be equal to theta, because if we kind of extend the plane here, it'll look like this. Here's theta. Again, and this is a little bit of a messy picture, but if we look at it, this part of the diagram is going to be a right angle. I'm going to redraw that. So we know that this angle here is going to be, because we have another right triangle, this angle that I just drew is going to be 90 minus theta, and then we have a straight line here, which is 180. 180 minus 90 for the right angle gives 90 between the angle that I just drew and the angle we're interested in. And since we know that the angle that I just drew is 90 minus theta, if we have 90 minus 90, the point is, by doing a little bit of just analysis, we'll find that this angle here is equal to theta, which helps us figure out what relationship between theta and FG gives us the parallel component. So since this is our right triangle here, we have our theta, and we're looking at the component that is opposite of theta. That means that the parallel component is going to be equal to FG times sine of theta. And that is the important part. The parallel component of FG is equal to FG sine theta. And since we know that T and FG sine theta have to balance because the box isn't moving, we can say that the magnitude of FG sine theta is equal to T. Now, that's great. We have our expression for T, except we don't know what FG is. We don't have FG is not one of the variables that were given at the beginning. So we have to rewrite that using variables that we can actually use in our answers. And of course, FG is going to be equal to the mass of the box times the acceleration due to gravity. So that makes T equal to big M times G times sine theta. That gives us our answer for part C. Oop, scroll down a little too far. So now moving on to part D. Here we are trying to figure out what the full length of the string is. We're only given h as a value that we can use, the height of the vertical part of the string. But we are modeling the full length of the string as one leg and the hypotenuse of a right triangle. So I'm going to draw our right triangle. Here's theta. Here's h, and we're going to call the hypotenuse c, because a squared plus b squared equals c squared. So we know that h is going to be the vertical component of c squared, or the vertical component. If we draw this as a vector, it would be the vertical component of c. So we can say that c times sine of theta is equal to h, because h is opposite of theta. So we have the hypotenuse, and then we take the vertical component, or the component opposite the angle, sine theta, to get h. But what we can do is we can rearrange this to say that c is equal to h over sine of theta. And this is helpful because the total length of the string is going to be, I'm going to call this cursive L, is going to be equal to h plus c. So then we can rewrite c as h over sine theta, and then we get this expression as just using symbols that we're able to use that are established for us in this problem. So that then gives us that L is equal to h plus h over sine theta. And so this is a perfectly fine answer for this part of the problem. This is, I think, the neatest way to write it. But I am going to do a little bit of rearranging to make the next parts of the problem a little bit easier. So we're actually going to say, we're going to factor out h from both terms. So we get h times 1 plus 1 over sine theta. And then we're going to write the part in parentheses as a single fraction. So 1 is going to be equal to sine theta over sine theta. And then we can put that as a single fraction. That'll give us that L is equal to h times sine theta plus 1 over sine theta. And so this is a little bit less intuitive than what we had before, but it will make the next parts of the problem much easier. So this is what I wrote down as my final answer for part D, but we'll use this last bit, the h times sine theta plus 1 over sine theta, in the next parts of the problem. So now we move on to part E. And in this part, we want to find mu, the mass per unit length of the string. And so that is going to be equal to the mass of the string, little m, divided by the total length, cursive L, which is easy enough. So we'll just take the, we'll substitute in for cursive L, h times sine theta plus 1 over sine theta. So that gives us m divided by h times sine theta plus 1 over sine theta. And then, since we have sine theta, which is in the denominator of the denominator, we can go ahead and flip that up to the numerator, and that'll give us m times sine theta divided by h times sine theta plus 1. And if we had used what I wrote down as the final answer for D, the more simple version, then starting here, these answers would get more and more ugly. So that's why I rewrote it with this different form. So our final answer for E is m sine theta over h times sine theta plus 1. Now we'll move on to part F. In part F, we want to find the speed of the waves in this string. So V, since we're dealing with a string under tension, we can say that the speed of the wave is equal to the force of the tension divided by mu. And we have formulas for both T and mu. So we go ahead and just plug those in. So then V becomes the square roots of, and our formula for tension is big M times G times sine theta. And that is all divided by our formula for mu, which is m sine theta divided by h sine theta plus 1. I'm going to put that in parentheses because that's a whole term on its own. And if we go ahead and start simplifying this, we'll get we'll have mg big M times G times sine theta times h times sine theta plus 1, and all of that is divided by sine theta, or m sine theta, little m. And all of that is under square root. And we can keep simplifying this. We have a sine theta in both the numerator and the denominator. So we can take those out. And then our final result for velocity v is equal to big M g h times sine theta plus 1 divided by little m. And all of that is under the square root. And so that's our answer for part F. And we just got 3 more to go. So thank you for sticking with me. So G, part G, we want to find what the fundamental frequency of the vertical part of the string is using symbols. So we'll call this fundamental frequency F sub h, for h, the vertical part of the string. And that is going to be equal to its velocity divided by its wavelength. And the wavelength, of course, is going to be twice the height because we have a node at both ends. So we go from a node to another node. That'll be half a wavelength. To get to a full wavelength, we have to go twice that distance. So lambda is equal to 2h. I'll go ahead and write that in here. And then v, of course, is what we had in the previous problem. So what we end up for our formula for this frequency is going to be equal to 1 over 2h times our formula for v, which is the square root of big M g h times sine theta plus 1. All of that divided by little m. And we'll complete the square root there. And we can start simplifying this a little bit. So we have an h inside the square root in the numerator, and then we have an h outside the square root in the denominator. So we can go ahead and bring that h into the square root in the denominator as an h squared. And so we'll rewrite that as 1/2 times the square root of big M g h sine theta plus 1 all over little m h squared. So then the h in the numerator gets canceled out, and then the h squared in the denominator just becomes an h. And then I'll go ahead and rewrite this, but that is our final answer for part G. So FH is equal to 1/2 square root of big M G H, or sorry, just big M times G times the square root of sine theta plus 1. And then all of that is divided by little m times h. And there we go. So that's our answer for part G. And then part H, we are given numerical values for big M, little m, h, and theta, and we need to figure out what f of h is numerically for these values. So I'll go ahead and write down the values for all the variables. So big M is equal to 1.50 kilograms. Little m is equal to 0.750 grams, which is, of course, 0.000750 kilograms. And then h is 0.500 meters. And theta is 30.0 degrees. And so what we do is we just plug in all of these values for the variables into our formula for part G and plug it into our calculators and evaluate it. So we just take our formula for part G, 1/2, and plug in all the variables. So we have our square root. And then big M is 1.5 kilograms times G, which is 9.80 0 meters per second squared times sine of 30 degrees, 30.0 degrees, plus 1. And then in the denominator of our square root, we have little m, 0.000750, times height, 0.500. And you plug that into your calculator, and you should get the result of 121 hertz as our fundamental frequency for the vertical part of the string. Now, we can move on to part I, and we are almost done. And now we want to figure out what the fundamental frequency is for the part of the string that's over the inclined plane. So from the pulley towards the mass big M. So for this, we again have the formula for the fundamental frequency. This time I'm saying it's Fc since we called that part of the string C earlier. So Fc is still equal to, the speed of the wave over the wavelength, but now the wavelength is different because the length of the string is different. We can still say that it's bound at both ends, and so it's going to have a node at both ends. It'll have a node at the pulley and where it's tied to the weight, so it'll still be twice the length, but now the length is C. But if we recall from earlier, so lambda is equal to 2c, but if we recall from earlier, c is equal to h over sine theta. So lambda becomes 2h over sine theta. And the string has not changed. It's still under the same tension and still has the same mu, so our v stays the same, thankfully. So that allows us to have a lot of the work done already. So then Fc becomes 1 or sine theta over 2h, because we have 1 over lambda, and lambda is equal to 2h over sine theta, so we just take the reciprocal of that. And then all of that is times v, which of course is mgh, big M, times gh, times sine theta plus 1. Then in our denominator of the square root, we have over m8. Sorry. Don't have h in the numerator, we have h in the denominator. So our square root is square root of big M times g times sine of theta plus 1. And all of that is over mh. And here we want to find the numerical value again, so we're using all the same values as the variables before. But if we take a quick look and compare Fc, our formula for Fc, to our formula for Fh, we see that the only difference is this sine theta in the numerator before, at the very beginning. And before we just had a 1 in the numerator there, but now we have a sine theta. So what we can say instead is that Fc is actually equal to sine of theta times Fh, which saves us a ton of work because we already know what Fh is for these values that we're using. We already know that Fh is 121 hertz. So we can go ahead and just evaluate this formula. Sine theta will be sine of 30 degrees, and times Fh, which is 121 hertz. Sine of theta, or sine of 30 degrees, of course, is just 1/2. So we'll end up with 60.6 hertz for our answer, which makes a lot of sense if sine of 30 is 1/2. And there you go. That's how you do this problem.